This content is brought to you by Mazunda Academy.
Hello everyone. Today in this lecture we will see tree and its application. So tree is a topic that is generally studied by discrete structure or discrete mathematics students. So let us see the concepts and other applications of tree. So in the subsequent part of our lecture, first we will study what is tree and rooted tree, then what are the different properties of tree, then we will see what is terminal, vertex, or leaf, then internal vertex or branch vertex. After that we will see basic terms on rooted tree. So what are the different terms that we will cover? What is level of a vertex, what is height of a tree, then children, then parent vertex, siblings, ancestors and descendant. These are the concepts that we will study in a rooted tree. After that we will understand what is a subtree and simple applications of tree like binary tree and full binary tree. We will see how a mathematical expression can be stored. Okay, and then we will see some exercise question. Now let us start formally. So what is a tree? A tree is a connected undirected graph with no simple circuit. What is the meaning of no simple circuit? First of all, a tree must be connected. This is the first condition, that this graph, whichever we will check for whether it is a tree or not, the graph must be a connected graph. Then no simple circuit means there cannot exist any loop or cannot exist multiple edges. Multiple edges cannot exist and loop cannot exist. Then circuit cannot form, like we cannot have this form of situation in the graph where there is a closed path between any two vertices. I mean, if you see, if we can find a closed path between a pair of vertices, then this graph will not represent a tree. So these are the points you will keep in mind while identifying a graph whether it is a tree or not tree. So as an example graph of tree, if I draw, so like for example, this is a vertex, this is another vertex, this is another vertex, say there are three vertices, and this is one edge, this is another edge. So this is a tree. And how many vertices here? Number of vertex n is 3 and number of edges is 2. Next we are taking some of the example graph to check whether they represents tree or not. So if we take the first graph G1, we will check all those points like whether it is a connected graph. Yes, it is a connected graph. All the vertices are connected. Connected means there exists a path from any vertex to any vertex. Then it is a connected graph. Then do you have any loop? No. Do you have any multiple edges? No. Is there any closed path exists? I mean circuit exists? No. Therefore G1 is representing a tree. Now come to G2. If we talk about G2, then G2 you can see there is a crossing in the edge AF with BE, but this crossing can be avoided. Like if we rearrange the vertex, like vertex B, if we shift it somewhere here say for example, if we shift B vertex here, then the edge BE will come like this. In that case, this crossing will be avoided. So we can avoid this crossing, and finally we can check this edge is not there no more. Okay, this vertex also shifted. Now we can see all edges are not crossing, which is not a required condition, but all the vertices are connected. There is a path between any two vertices. And second point is there is no circuit, there is no loop, there is no multiple edges. Therefore, G2 also a tree. Come to G3. Now G3, some crossings are there. We can avoid this crossing. For example, if we shift D from here to somewhere here in this area, then this crossing can be avoided. But after that also you can see there will be a closed path from A to B, then B to E, then E to D, and then D to A. That means a cycle exists here in this graph. The graph is connected, no multiple edges, no loop, but there exists a circuit, closed path. Therefore, G3 is not a tree. Then G4, if we see, in G4 actually it is a crossing of the edge, but we can avoid this by shifting the position of the vertex. Say F vertex, if I bring here, then this crossing will be avoided, and we can see the graph will become a disconnected graph. That means there is no path between A to B. There is no path exists in the graph G4 from A to B. So graph is a disconnected graph. Therefore, any disconnected graph does not represent a tree. So here, what is the conclusion? G1 and G2 are trees. G3 and G4 are not trees. Next, there is a result or theorem, you can say. An undirected graph is a tree if and only if there exists a unique simple path between any two of its vertices. Already we understood with the example. Next, we will see a rooted tree. What is a rooted tree? In the name itself we can understand. That means in the tree there should be a vertex which is designated as root. So a rooted tree is a tree in which one vertex has been designated as the root and every edge is directed away from the root. So every vertex should be connected with the root through some path, and that path will be a unique path. So this is an example of rooted tree. So we can see here A is the root. In general, we write the root at the top and then all other branches we write at the down, okay, below the root. So let us proceed further. So here A is the root of the tree T. Next, we will see some of the properties of tree. So the first property is a tree with n vertices has n-1 edges, where n is greater than or equal to 0. Let me draw a tree. Say for example, this is a tree with 3 vertices. So here, how many vertices? N equal to 3. And how many edges? Number of edges is 3 minus 1, that is 2 edges. And we can see edge 1, edge 2. There are 2 edges and 3 vertices. Say V1, V2 and V3. So if the graph is a tree with n vertices, then it has n-1 edges. So this is a very important property. Next, any connected graph with n vertices and n-1 edges is a tree. That means this is the rephrase of property number 1. Because why this rephrase is important for us? Because if any multiple choice or short question asked with rephrasing, you should understand and choose the correct option. Next, a tree is connected, but if any edge is deleted from it, then the resulting graph is no more connected. It will be a disconnected graph. And we can easily see, suppose if we delete in this graph, if we delete edge 2, then the graph will become disconnected because V3 will be an isolated vertex. There will be no connectivity or no path from V1 to V3 if we delete the edge 2. So that is the explanation of property 3. Next, any tree that has more than one vertex has at least two vertices of degree 1. For example, in the example graph that I have considered, how many vertices here? N equal to 3. Now, the property is saying any tree that has more than one vertex. So obviously it is satisfying because number of vertices 3. Has at least two vertices of degree 1. That means minimum there will be two vertices of degree 1. Degree means number of edges connected to that vertex is 1. So we can see here exactly two vertices in this graph which are of degree 1, that is V2 and V3. Next, we have a graph is a tree if and only if there is unique path between any two of its vertices. So that is already we have understood. Next, let us see an example. Explain why graphs with the given specification does not exist. First question, a tree with 12 vertices and 15 edges. Second question is a tree with 5 vertices and total degree of 10. Answer number 1. We know any tree with 12 vertices will have 12 minus 1 equal to 11 edges, not 15. Just now we have seen for any tree with n vertices, number of edges will be n minus 1. So here your n equal to 12, so the number of edge will be 11. But as per the question it is 15 edges, so which is not possible. Second question is a tree with 5 vertices and total degree of 10. So here you can see any tree with 5 vertices will have 5 minus 1 equal to 4 edges. This is very clear. And if 4 edges, then we know from the handshaking theorem the total degree. What was the handshaking theorem? Sum of all the degree of its vertices equal to twice the number of edges. So this is your E, number of edges 4. So sum of all the degrees, that is your total degree. Total degree. So total degree means the sum of all the degree of the vertices is twice the number of edges. So 2 times number of edges means 2 multiply 4, that is 8. But as per the question, total degree is 10. So in both the situation, in both the questions, such tree does not exist. Next we will see what is terminal vertex or leaf, and then internal vertex or branch vertex. So a vertex of degree 1, exactly 1, in a tree is called terminal vertex or leaf. And a vertex of degree greater than 1, it can be 2, it can be 3, or it can be any number, that vertex is called internal vertex. So terminal vertex means what? The vertex of degree 1. Internal vertex means the vertex of degree bigger than 1 or greater than 1. Terminal vertex, sometimes it is called leaf, and internal vertex, sometimes it is called branch vertex. Now let us see an example tree. So for example, in this tree, if I just talk about D, so D is of degree 1, therefore it is a leaf vertex or terminal vertex. So what are the terminal vertex here? D, E, F, K, I, L, M. These all vertices are of degree 1, therefore they are terminal vertices, and remaining all vertices including the root, they have degree greater than 1, and therefore they are branch vertices, or you can say internal vertices. So I have written here in this tree, these are the terminal vertices and these are the internal vertices. Next, what are the basic terms on a rooted tree? So first we will see these all: level of a vertex, height of a tree, parent vertex, child vertex, siblings vertices, ancestor vertex, descendant vertex. These all concepts on a rooted tree we will understand one by one. Let us start. What is the meaning of level of a vertex? So level of a vertex is the number of edges along the unique path between the vertex and the root. For example, say you consider H. You want to know what is the level of H. So from the root, you see there will be an unique path, only one path that will reach to H. And you count how many edges required, how many edges connected from root to that vertex. So 1 and 2. 2 edges connecting root to the vertex H. Therefore, level of H is 2. So we can see here in this tree, level of A means root. Level of root is 0 because there is no edge connected from the root to root. Then level of B, this one is 1. Obviously level of F, level of G, all are of level 1. Then level of C is 2. There are 2 edges. So C, H, I, J, these all are the vertices of level 2. And D, vertex D is of level 3 because 3 edges are on the path, unique path from root to the vertex D. So 1, 2, 3, and we can say D, E, K, L, M. These all vertices are at level 3. Next, height of a tree. Height means the maximum level exists in this tree. Okay, maximum level of any vertex that exists on this tree is called the height. So we can see if we individually, if we consider the level of each vertex, then the maximum level exists in this tree T is 3. So the height is 3. Next, parent vertex and child vertex. Let us see the definition first. Let V be a vertex in a rooted tree T other than the root. Say for example, I am considering say H, this vertex as my V in the definition. Okay, this is V. Then a vertex U will be a parent of V along the unique path from V to A. Say for example, which vertex is falling along the unique path from H to A is G. And the condition here, the level of that vertex I have mentioned as U, so U will be G here. Okay, so the level of U must be 1 less than the level of V. In that case, V is the child of U, U is the parent of V. So in this graph, So vertex B is the parent of C and C is the child of B. Next we will see what is siblings. So siblings, vertices, in the name itself we can understand brother sisters, okay, they are siblings. So let us see the definition. Any two vertices or more than two vertices, they will be treated as siblings if they have the same parent. For example, here H, I and J, they all have the same parent G. So H, I and J, they will be treated as siblings. So whatever I said. Next, ancestor and descendant vertices. What is ancestor? Ancestor means for vertices V and W, if V lies on the unique path between W and the root, then V is the ancestor of W and W is the descendant of V. For example, let me choose this K, one vertex, and we can see here along the unique path from K to the root, G is falling, H is falling. So H, G, these are what? These are the ancestors of K. And we can say H is a descendant of G, K is a descendant of G, K is a descendant of H. This is the concept. Then subtree. In the name itself we can understand sub means part. Okay. So a subtree, if A is a vertex in a tree, the subtree with A its root is a subgraph of tree consists of A and its descendants and all edges incident to this descendant. So for example, if we consider that say C is the vertex and C will be the root of the subtree of this tree capital T, then this will be the subtree where C is the root and all its descendant along with the edges incident on it. So this will be the subtree rooted at C. So for example, the subtree rooted at G is shown in figure 6. So here we are considering subtree rooted at G. So this all part will be a subtree rooted at G. Next, binary tree and full binary tree. Bi means 2. Okay, so see the definition. A binary tree is a rooted tree in which every internal vertex has at most 2 children. Every child in the binary tree is designated either as a left child or right child, but not both. So in the name itself we can see something like this. If this is a tree, I have example graph. So if you have something like this, then it is a binary tree, and you can see there are at most maximum 2. So for this is the root, it has 2 child, and then this is the next child, it has only 1 child. Okay, so a binary tree is a rooted tree. There must be a root designated vertex and every internal vertex has at most 2 children. So this is an internal vertex because it's degree 2 and it has 1 child. At most 2, maximum it can be 2, it can be 1 also. It cannot be 0 obviously, because if it is 0 then it will not be a internal vertex, it will become a leaf vertex. Next, this is an example. So we can see this example, it is a B C D E F and this is a binary tree. Then a full binary tree. What is a full binary tree? A binary tree is said to be a full binary tree if each internal vertex has exactly 2 children. Like this is an example. This previous graph here you can see it is not fully binary tree. Why not full? Because the internal vertex C does not have two children, only one child, so it is just a binary tree. But a full binary tree means every internal node must have two children. So we can see in the graph every internal node including the root have two child, therefore it is a full binary tree. Now some results or theorem which are very important. So the first one is, if k is a positive integer and t is a full binary tree with k internal vertices, k represents the internal vertices, then the tree T has total 2k plus 1, that is your n, number of vertices n equal to 2k plus 1, where k is the number of internal vertices. And for that binary tree, I mean full binary tree, it has k plus 1 terminal vertices. So generally terminal vertices we denote by small t. So in a full binary tree with k internal vertices, the total number of vertices will be 2k plus 1 and total number of leaf vertex or terminal vertex will be k plus 1. So these two results very important in our subsequent part. Next result is, if T is a binary tree, not necessary to be full binary tree, okay, then and T is the terminal vertices, then and H is the height, then number of terminal vertices must be less than or equal to 2 power h. This result also we will use in many exercise questions. If T is a binary tree, not necessary to be fully binary, just a binary tree, and it has T number of terminal vertices and height h, then T always less than or equal to 2 power h. That means number of terminal vertices always less than or equal to 2 power h, where h is the height of the tree. The maximum number of terminal vertices in a binary tree can be 2 power h, okay, from here. And there are example graph, you can apply this and you can check it here. So this one, it is a maximum, I mean full binary tree. The second graph here, second tree, and you can see what is the height of this, h equal to how much, 2. So the total number of terminal vertices will be t equal to 2 power 2, that is 4, and you can see 1 2 3 and 4, there are 4 terminal vertices. And this one, if we apply the same one here, what is your h, height is 2, and therefore the number of terminal vertices t equal to, it should be less than or equal to 2 power 2, that is equal to 4. That means the number of terminal vertices must be less than or equal to 4. So how many here, 1 2 and 3, so 3 is less than 4, that means it is true. Next we will see an example. Explain why graphs with the given specification does not exist. First question is, a full binary tree with 9 vertices and 5 internal vertices. Second question is, a binary tree, height h and 18 terminal vertices. Okay, so let's start answer one by one. The first one is, it's a full binary tree, remember it's a full binary tree, and 9 vertices, that means n equal to 9, n equal to 9, and 5 internal vertices, that is k equal to 5. Now Number of terminal vertices will be k plus 1 as per the rule just now, because it is a full binary tree. So number of terminal vertices should be 6, and in the question it is said what? 9 vertices and 5 internal vertices. Now how many internal vertices can be? So the total number of vertices is 2 multiply 5 plus 1, that is 11, which is a contradiction. How it is a contradiction? Because what is given here? N equal to 9 vertices and 5 internal vertices and k equal to 5. We know as per the result, as per the rule of full binary tree, if full binary tree with k internal vertices, then 2k plus 1 total vertices. So in that case it must be 2k plus 1, that is 11. That means number of vertices must be 11, then only there can be 5 internal vertices. But as per the question it is said that 9 vertices, so it is a contradiction between them. If this is true, this cannot be true. If this is true, this cannot be true. So it's a contradiction between that number of vertices in the graph. Therefore such graph does not exist. Okay. Next, in the second question what it said, a binary tree with height 4, that is h equal to 4 and 18 terminal vertices. So just now we have seen the number of terminal vertices t in a binary tree, it must be less than or equal to 2 power h, that means 2 power 4, that means equal to 16. That means number of terminal vertices must be less than or equal to 16, but in the question it is given 18, which is not possible. So no such graph exists. So the explanation I have written here, you can easily understand it. Next, simple application of binary tree and full binary tree. Now representing algebraic expression. Now say we have an expression of the form, for example, a divide c plus d, this one. So generally how we represent this algebraic expression using binary tree, the operators divide, plus, whatever, they will represent the internal vertices. They will be represented by internal vertices, and those variables a, b, c, d, whatever, those variables will be act as terminal vertices. So we have written here the operators. This is the root, obviously this is the top operator. The terminal vertices are the variables a, b, c, and a, c and d, and the internal vertices are arithmetic operators plus and root. Okay, that is divide. Let us see an example, proper example. Draw a binary tree to represent the following expressions: a divide b minus c multiply d. So as already I said, internal vertices are the arithmetic operators and the terminal vertices are the variables, and the operators at each vertex acts on its left and right subtree in the left to right order. This is important, left to right order. For example, here you can see in this, so root will be the divide will be at the root, and its left subtree will be a, and this all will be in the right subtree. This all in the right subtree. Now when you are going to place this again among them, this minus will be in the next root of the subtree, so minus here, and then left will be b and right will be c multiply d. They will be in the right. Again, while placing c multiply d, multiplication will be at the root and c will be at the left and d will be at the right. So this is the representation of the algebraic expression using a binary tree. Next, we are moving towards the exercise. So these exercise questions I have taken from the very famous book Discrete Mathematics and Its Application by Kenneth H. Rosen, and this exercise copied from that book with a proper justification that it is only for study purpose without violating any copyright law. Our intention is just to help students only for study purpose without any intention of commercial activities. Okay, let's start. The first question here, which of these graphs are tree? So as already we understood before while studying the tree, the first one will be a tree because it is a connected graph. There is no cycle, there is no loop, there is no multiple edge, therefore it is a tree. Then B cannot be tree because it is disconnected graph. Then C is a tree although the edge is crossing, but we can avoid this crossing by rearranging the edge and vertex position. So this will also be a tree. D cannot be tree because there is a cycle. There is a closed path exists between these vertices. So D cannot be a tree. E can be a tree, no problem. This will be the root. Okay, this can be the rooted tree. It can be considered as a rooted tree, and there is no loop, no cycle. Okay, no multiple edge. So E is a tree. F cannot be tree because it is a closed loop. It's a closed loop or closed path. Okay, so this cannot be, or you can say it is a cycle. So F cannot be a tree. So the answer I have written here: A is a tree, B is not a tree because it is disconnected, C is tree, D is not a tree because it contains a circuit, and E is tree, F not a tree because the graph contains a circuit or cycle. Next, few more example questions which are a tree. So obviously A is a tree, then B is also a tree, C is not a tree because it is disconnected. If we just rearrange this vertex somewhere up or this somewhere down, then it will be clearly disconnected. And D is connected everything, no cycle, no loop, no multiple edges, therefore it is a tree. E is not a tree because it contains a cycle, one or two cycle minimum. If one cycle, then it is enough. And this one, F, is a tree because it is connected, and we can avoid the crossing by rearranging the position of the vertices and edges. So the answer: A is a tree, B is a tree, C is not a tree because the graph is disconnected graph, D is a tree, E, it is not a tree because the graph contains a circuit or cycle, and F is a tree. So hope you understand now how to identify tree, whether a graph is a tree or not a tree. Now we will move little further about the exercise questions. So there is an example graph attached with the question, and we have to answer a few number of questions based on this graph. So first question is, which vertex is the root? So here the root is obviously, this is the root. Root is the A. So the answer is A is the root. Next question is, which vertices are the internal vertices? So if you remember what is internal vertices, vertex of degree more than 1. So this is degree more than 1, this is more than 1, this is the degree more than 1, this vertex of degree more than 1, this vertex of degree more than 1, this vertex of degree more than 1, then this, then this. So B, C, F, H, D, J, Q, T, these are the internal vertices and they are of degree more than 1. Next, which vertices are leaf vertex? Leaf vertex means the degree equal to 1. So obviously this is 1 and this all vertices of degree 1, this is of degree 1, this is of degree 1, this is of degree 1, degree 1, degree 1, degree 1, degree 1, degree 1. So these are the different vertices of degree 1. Which vertices are children of J? So if we see, if we go to J vertex, its children are Q and R. Clearly, okay, Q and R are the children of J. So Q and R. Next question is, which vertex is the parent of H? So H vertex here, this is H, and the parent of H is C. C is the parent of H. Then which vertex or which vertices are siblings of O? So your O is here. Sibling means the vertex which have the same parent. So P and O, they have the same parent, therefore P is the sibling of O, or O is the sibling of P. Next question is, which vertices are ancestors of M? So vertex M is here, this is M. Ancestor means all the vertices which are falling on the path to the root. So if I see the path to M, so it is going like this, then going to the root. So along this path, F, B, okay, F, B and A, they are the ancestors of M. Next question is, which vertices are descendant of B? Descendant of B means from B down the line, what are the vertices? So you can see the descendants of B are E can be one of the descendant, then F can be one of the descendant, then L, M, N. These all the vertices are down the line of B. So they are descendant of B. Next question is, you can see, is the rooted tree is a full m-ary tree for some positive integer m? Like binary means 2-ary. If m equal to 2, then it is binary. Okay. Now, is it full binary or full m-ary? Full m-ary means for some positive integer m, is it, that means whether this tree, all the internal vertices have exactly m number of children for some positive integer m. But it is not true. Why? We can see here how many children of B? 2. But how many children of F? 3. Not same. It must be same number of children everywhere. Here A have 3 children, but again C have 2 children, H have 2 children, D have 3 children. So sometime 2, sometime 3. Therefore, this tree is not a full m-ary tree for some positive integer m. Now, some definition. When we say m-ary tree, a rooted tree is called m-ary tree if every internal vertex has no more than m children. A tree is called full m-ary tree if every internal vertex has exactly m children. And obviously I said as before, if m equal to 2, then it is called a binary tree. That means if there are exactly 2 children, then it is called either fully binary tree or binary tree, depending on the definitions. So next question that we are going to see, what is the level of each vertex of the rooted tree. Now level, if we speak, level of A, that is root. Is there any edge which is connecting the root to the root? No. So the level of A will be 0. Next, level of B. How many edge connecting this vertex B to the root? Only 1. So the level of B will be 1. So B, C and D, they all are of the same level 1 in this rooted tree. Next, if we see, for example, E. E, how many edge needed to required? I mean, how many edge connecting this edge E to the root? 2 edges. So level of E will be 2. Similarly, E, F, G, H, I, J, K, they all are of the same level 2. Next, if we go to the next level, say L. L is connecting by 3 edges. So L is at level 3. L, M, N, O, P, Q, R. They all are at level 3. S and T will be level 4. U will be level 5. Because you can see U is connected by 1, 2, 3, 4, 5 edges. Therefore, U is at level 5. So the answer I have written here, A is at level 0, B at C all. Okay. The details I already explained, so you can just check. Next question is, draw a subtree that is rooted at A. The subtree of this tree rooted at A, that means the tree itself, because subtree means all the descendants along with all the edges to that particular vertex, that is the subtree with that tree. So here the subtree rooted at A is the tree itself. Then draw a subtree that is rooted at C. So at C means this will be the subtree. So we can see the subtree here. Next, draw a subtree that is rooted at E. E means this one. Now in this case there is no descendant. So this will be just a vertex, isolated vertex without any without any children. So E is a leaf node, so the subtree has only vertex E, and it looks like this. There is no children of this subtree. Next question is, draw a graph with the given specification or explain why no such graph exists. The question here, full binary tree with 5 internal vertices. So answer here, k equal to 5. Internal vertices means k equal to 5. So if k equal to 5, then how many total number of vertices? N will be 2k plus 1. That means equal to 11. Total number of vertices 11. And number of terminal vertices will be k plus 1 as per the rule. That means 5 plus 1, that is 6. So one such graph is I have drawn here. You can also try a similar way. There should be total 11 vertices and the number of leaf vertex or terminal vertex should be 6. And at the same time it must be a full binary tree. Full binary tree means every internal vertex must have exactly 2 children. You can rearrange the vertex positions and you can draw another graph. Next question is, full binary tree, 5 internal vertices, 7 terminal vertices. So t equal to 7. Terminal vertices 7, internal vertices 5, that is k equal to 5. And it's a full binary tree. So if it is a full binary tree, then n number of vertices must be 2k plus 1. 2k plus 1, that means it is 11. 2 multiply 5 plus 1, that is 11. And terminal vertices 7. Okay, now see the answer. For a full binary tree, the number of terminal vertices must be k plus 1, that is t must be equal to 5 plus 1, that is 6. But in the question it is given 7 terminal vertices, which is not possible. Next question is a full binary tree with 7 vertices, so that means n equal to 7, of which 4 are internal vertices, so k equal to 4, therefore number of terminal vertices will be k plus 1, that is t is 5. So the answer is here n equal to 7. For a full binary tree, n equal to 2k plus 1, that is k equal to 3 internal vertices. So if n equal to 7, then the rule is for a full binary tree n equal to 2k plus 1, that is k must be 3, but in the question it is given k 4. 7 vertices, full binary tree of which 4 are internal vertices, that is they are telling that total number of vertices 7, and it is a full binary tree where 4 internal vertices. So as per the rule it is not possible, because as per the rule, if there are n vertices and it is a full binary tree, then n must be equal to 2k plus 1. So using this rule we can work out, and finally we can get k equal to 3, but they are mentioning k equal to 4, so no such graph exists. Okay, so not possible. Next, a full binary tree with 12 vertices, you can see here, so n equal to 12. Okay, and since we have 2k plus 1 is your n, so from here if we work out, then n equal to 12, and we can say 2k equal to 12 minus 1, that is 11. This implies k equal to 11 by 2. So this is a fraction, so the number of internal vertices cannot be a fraction, right? So this is one way. Another way, as I have answered here, you can see for a full binary tree n equal to 2k plus 1, and 2k plus 1 is always an odd number, but they are telling a full binary tree with n equal to 12, which is an even number. That means it is not possible. So either way you can explain like in terms of k or in terms of n. Here the explanation is given in terms of n, and if you want to put your argument in terms of k, that is internal vertices, you can write that k, number of internal vertices, coming out to be fraction, which is not possible. Therefore no such graph exists. Second question is, next question, full binary tree with 9 vertices, here n equal to 9, and therefore how many internal vertices will be? 2k plus 1 will be equal to 9. So from here k will be equal to 9 minus 1, 8 by 2, that is 4. So total 9 vertices and 4 internal vertices, and it must be a full binary tree. So this is the situation for me. Okay, for a full binary tree, this implies k equal to 4 internal vertices, and one such tree is, this is the drawing. You can try, you may get another looks of the tree. Okay, but it must be a fully binary tree with 9 vertices, and there must be 4 internal vertices. We can see B, A, C and G, these are internal vertices. Next question is a binary tree, height 3, 7 terminal vertices. So what is given? Given h, height h equal to 3, and what is given? Terminal vertices t equal to 7. Now what is the rule for me? Number of terminal vertices t must be less than or equal to 2 power h. This is the rule for a binary tree. So is it satisfying? Say for example, In my case, t less than or equal to, it should be 2 power 3, that is 8. So number of terminal vertices must be less than or equal to 8, but given one is 7, so it is satisfying this condition. So such graph possible. Okay, so here h equal to 3 equal to t equal to 7 for a binary tree, t less than equal to this, so such graph is possible. One such graph can be, it is just a drawing by your own. So total, you can see how many terminal vertices, h. Okay, and it is not necessary to be fully binary, it is just a binary tree. Okay, now you may ask that how many vertex I should add. There is no restriction assigned in this question, but when you will put that 7 terminal vertices, automatically the number of vertices, so you start from here, from the leaf vertex, it should be 7 in such a way. So use pencil, and some rearrangement sometimes somewhere may be needed, so you just try and make a tree which satisfy the conditions. So you can see here there are level, maximum level is 3. Okay, I mean height of the tree is 3 and number of terminal vertices are 7. These are the two conditions. Next question is a full binary tree, height 3, 6 terminal vertices. So you can see the question here, h equal to 3 and t equal to 6. As we know, number of terminal vertices must be less than equal to 2 power 3, and that is equal to 8. So t less than or equal to 8 and my given condition t equal to 6, so it is fine. Okay, so let us see the answer. Here h equal to 3 and t equal to 6, so for a binary tree t less than equal to this, so such graph possible, and it must be a full binary tree, remember. So one such graph is, you can see here, level is 3 and number of terminal vertices 6, 1 2 3 4 5 6, and you can see every internal vertices have 2 children, therefore it is a full binary tree with level 3 and 6 terminal nodes. Next, a binary tree, height 3, 9 terminal vertices. It is given h equal to 3 and terminal vertices t equal to 9. Now as per the rule, the terminal vertices must be less than or equal to 2 power h, that is 2 power 3, and that is equal to 8. But my given number of terminal vertices is 9, but as per the condition it should be less than or equal to 8. So it is a contradiction with the result, with the theorem or rule. Therefore no such graph can exist. So you can see the answer here. Here h is 3, t is 9. For a binary tree, t less than this, so a binary tree with height 3 and 9 terminal vertices is not possible. Okay, thank you. So that's all for there are many more exercise questions available, and you can see some of them from YouTube or from any other source or from the book. Even there are many questions in the book, in this Rosen book, which is easily available online, or in our library it is available, so you can go ahead and study. So thank you so much.
Please like, share, and subscribe our YouTube channel. Hit the bell icon to get the latest update.